All right, let's jump right into this explainer. Today we're doing a full autopsy on material failure. We're going to look at exactly why things break, shatter, and tear apart when they're under pressure. Did you know that the annual economic cost of material fracture in the US alone is estimated in the hundreds of billions of dollars? It's wild. And honestly, almost every major engineering safety regulation we have today was written in the immediate aftermath of some catastrophic failure. So for those of us studying engineering, understanding this isn't just some academic exercise, right? It's literally the foundation of safe, reliable design.
And this right here brilliantly illustrates the life-or-death stakes we're talking about. Over on the left, you've got a World War II-era Liberty ship that literally just split in half while sitting in the harbor. Why did that happen? Well, they used a then-new welding technique that turned out to be dangerously susceptible to brittle fracture in the freezing Atlantic waters. Then, on the right, that's the devastating aftermath of Aloha Airlines Flight 243 that was explosive decompression caused by undetected fatigue and corrosion. You see, these aren't just little math errors, they're real-world disasters caused by fundamental material failures.
To make sure we don't repeat these disasters, we're going to follow this roadmap today. We'll start with the basic anatomy of structural failure, compare ductile and brittle fractures, translate that into the principles of fracture mechanics, and then wrap up with fatigue from cyclic stress and high-temperature creep.
Starting off with Section 1, the anatomy of structural failure. The crucial takeaway here is that all structural failure basically begins with a simple fracture.
At its core, simple fracture is exactly what it sounds like. It's just a material separating into two or more pieces under a constant static stress. It doesn't happen by magic. It's always the direct result of a crack propagating through the material. If you can understand how that crack moves, you basically understand the whole failure.
Moving on to Section 2, ductile versus brittle fracture. Depending on the material and the environment, propagating cracks behave entirely differently under pressure. There's just a massive contrast between these two modes. Ductile fracture is, well, it's almost accommodating. It gives us a slow crack propagation with a lot of massive plastic deformation. It stretches, it bulges, and crucially, it gives you a visual warning before it goes. Plus, ductile materials absorb way more strain energy before they fail. Brittle fracture, on the other hand, total opposite. It's a rapid, silent assassin. The crack rips through at high speed with almost no plastic deformation, so you get zero warning whatsoever. Boom, it's just gone. That's exactly why ductile fracture is generally much preferred in engineering design.
You can literally see this difference physically when you look at test specimens. Check out that classic drawn-out cup and cone surface on the left. That's your textbook hallmark of a moderately ductile break. The metal was basically desperately holding on, stretching out before finally letting go. And here's a neat detail. That cup and cone failure actually happens at a 45-degree angle to the tensile axis because it's driven by the maximum shear stress. Now compare that to the flat, granular, almost perfectly sheared face of the completely brittle fracture on the right. Night and day, right?
Scale this up to industrial pipes and the stakes become pretty terrifying. The ductile failure on the top took a massive hit of internal pressure, but look closely. It's still in one continuous piece, even after all that deformation. The brittle pipe on the bottom, though, completely shattered into countless sharp pieces. In pipeline engineering, a brittle failure isn't just a leak. It's basically a massive, high-velocity shrapnel hazard.
Let's zoom way in to the microscopic level and track this moderately ductile failure step by step. First up, the material starts necking, heavily deforming in one specific spot. This necking concentrates the stress locally, creating a runaway effect. Inside that neck, these tiny microvoids start to nucleate. As the stress keeps up, those voids grow, they coalesce, and they link together until an internal crack forms and shoots right to the surface.
This electron micrograph is amazing because it actually catches the crime right in progress. Look at the center of those craters. It shows us exactly where those tiny microscopic voids nucleate around hard inclusion particles inside the steel. These hard particles are usually just microscopic impurities left over from the manufacturing process, which really highlights why material purity is such a massive deal in metallurgy. As the softer metal pulls away from those impurities, empty voids are born, ultimately linking up into a catastrophic structural crack. Okay, Section 3, Principles of Fracture Mechanics. We need to translate all this visual evidence into mathematical reality. So, why do materials fail at stress levels way below what our theoretical calculations predict? Well, it's all about the flaws.
This diagram brilliantly shows how a seemingly harmless microscopic flaw actually amplifies the applied tensile stress right at its tip. It acts as a highly localized stress concentrator. If you look at the equation, the stress at the crack tip is driven largely by two things: the crack length, A, and the radius of curvature at the tip. If that radius is microscopically sharp, the amplified stress just skyrockets. It pushes the local material right past its breaking point, even if the overall load seems completely safe.
To fight this invisible threat, engineers rely on fracture toughness, denoted as Kc. This is a critical parameter that mathematically quantifies a material's inherent ability to resist brittle fracture, even when a crack is already in there. Because let's be real, in manufacturing, microscopic flaws are always going to exist. We have to design for materials that can tolerate them. Keep in mind, Kc depends on material thickness, temperature, and strain rate. In actual practice, engineers specifically look for the plane strain fracture toughness, known as K1C, to guarantee the most conservative, safest design possible.
Moving right along to Section 4, Fatigue and Cyclic Stress. If brittle fracture is the sudden assassin, fatigue is the slow, repetitive killer. The crazy thing about fatigue is how insidious it is. Even if your applied maximum stress stays perfectly and safely below the material's yield strength, lengthy, repeated stress cycling will eventually break it. To predict this, engineers use SN curves, which plot the stress amplitude against the number of cycles to failure. Now, for some materials like steel, there's a magic number on this curve called the endurance limit. It's a specific stress level where, if you stay below it, fatigue failure just won't ever happen, no matter how many millions of cycles it goes through. Yet, shockingly, even knowing this, dynamic cycling still causes roughly 90% of all mechanical engineering failures.
Here's one of the most classic mistakes a junior engineer can make: leaving a sharp 90-degree angle on a machine shaft. On the left, we saw how microscopic cracks concentrate stress, right? Well, on the right, we see that your macroscopic design choices do the exact same thing. You absolutely have to avoid sharp corners in your designs. That sharp angle acts as a massive stress concentrator that will literally slash the fatigue life of your part. Simply smoothing that out with a rounded fillet drastically drops the local stress and keeps your design off the wrong end of the SN curve.
All right, bringing us to Section 5, Creep at High Temperatures. Let's look at our final failure mode.
A creep is the slow, relentless deformation of a material under a constant stress in high-temperature environments, usually above 40% of the material's absolute melting temperature. Think jet engine turbine blades or high-pressure steam lines. This graph tracks its inevitable life cycle, plotting creep strain against time from the initial load all the way to a disastrous rupture. But, we can't exactly wait 20 years to test a turbine blade's lifespan in a lab. So engineers rely on time-temperature extrapolation models. The most famous one is the Larson-Miller parameter. It's a brilliant equation that lets us run short-term extreme heat tests to accurately predict a material's long-term creep life at normal operating temperatures.
Let's break down these three distinct stages of creep. First, you have primary creep. Here, the material undergoes strain hardening, so the actual rate of creep rapidly decreases over time. Then it stabilizes into secondary creep. This is the longest stage, and it has a steady-state constant slope, where strain hardening and recovery beautifully balance each other out. And then you hit tertiary creep. This is where the rate sharply and aggressively accelerates. Microscopic voids start linking up, the structural integrity collapses, and the part inevitably, catastrophically ruptures.
So we've seen how metals stretch, shatter, fatigue, and creep. And the common thread? Failure almost always starts at the microscopic level, hiding in tiny voids and invisible cracks. Knowing that mathematical perfection is a total illusion, your job isn't to build flawless machines. It's to build machines that survive their inevitable flaws. How will you account for those invisible cracks waiting in the dark? Keep that in mind the next time you're sketching a sharp corner. Thanks for joining me on this explainer.